Have you ever looked up at the night sky and felt that strange, quiet tug of curiosity? That sense that there's something more to all of this than meets the eye? What if I told you that the universe you see, the stars, the galaxies, the very laws of physics that hold it all together, might not be the first and only version of reality? What if our cosmos is just the latest draft in an endless cosmic library of forgotten worlds, each with its own story, its own rules, its own triumphs and failures? It sounds like science fiction, but some of the brightest minds in physics and cosmology are taking this idea seriously. They call them cosmic drafts, previous iterations of existence that may have risen and fallen long before our own universe even began. In this video, we're going to explore one of the most profound and haunting questions ever posed. Were there versions before this one? We'll venture beyond the limits of our observable reality and into the realm of cutting-edge theories, from cyclic cosmology and eternal inflation to quantum fluctuations and black hole paradoxes. We'll look for clues hidden in the oldest light in the universe, anomalies in the cosmic microwave background that just might be echoes of a cosmos that came before ours. And we won't stop at the science. We'll dive into the philosophy, the implications, and even the stories that help us wrap our minds around such an expansive idea. By the end of our journey, you won't just see the night sky differently, you'll feel it. You'll understand why some scientists believe our universe is fine-tuned for life, not by accident, but by evolution. You'll ponder whether time itself is cyclical, and if the echoes of ancient universes are still vibrating silently in the vacuum of space. This isn't just a story about physics, it's a story about us, about meaning, and about our place in something far grander than we ever imagined. So come with me, let's unravel the mystery of the universe's hidden drafts and ask together, what came before us? So what exactly are we talking about when we say cosmic drafts? It's a powerful metaphor that helps us wrap our minds around one of the most staggering ideas in all of science, the possibility that our universe isn't a one-off creation, but more like the latest version in an endless series of cosmic revisions. To really get it, picture a novelist working on a great book. The first draft might have a completely different ending. The second draft might introduce a character who later gets written out. Those early versions aren't the story, but they were essential steps in its creation, and a keen editor might still spot a faint echo of a deleted subplot in the final published work. Now scale that idea up to the entire cosmos. A cosmic draft could be a previous iteration of reality, a universe that existed before our own, operating under a completely different set of rules. Maybe in one draft, the force of gravity was twice as strong, causing stars to burn out in a cosmic blink. Perhaps in another, the number of spatial dimensions was greater, leading to a reality so complex and unstable it collapsed in on itself almost immediately. These aren't just parallel universes existing alongside us. The concept of drafts implies a sequence, a timeline of cosmic evolution where one universe might be the successor to another. This leads us to a fascinating theory proposed by physicist Lee Smolin, who suggested that universes could actually evolve through a process of natural selection. Think about it like this. Universes that have the right conditions to form black holes might, in turn, give birth to new universes inside those black holes, effectively reproducing. The child universes would inherit slightly tweaked physical constants from their parent. Over unimaginable stretches of time and countless generations, this cosmic evolutionary process would favor universes that are stable and long-lasting universes capable of forging galaxies, stars, and planets. In this breathtaking view, the fact that our universe appears so perfectly fine-tuned for life isn't a miracle. It's simply the result of a long and iterative editing process. We aren't living in a uniquely created masterpiece, but in the most successful draft so far, a version of reality that has been refined over and over until it could finally support beings like us who can look up and wonder how it all came to be. But if the Big Bang wasn't the true beginning, what was it? This is where the concept of cyclic cosmology completely reframes our understanding. Instead of a single, explosive origin story, this theory proposes that the cosmos operates on a rhythm of endless rebirth, a perpetual cycle of expansion, contraction, and renewal. Think of it not as a one-time event, but as a single breath in the life of an eternal being. Our universe expands outward for billions of years, galaxies rushing away from each other, but eventually the relentless pull of gravity takes over. All that matter and energy, now spread thin across the void, begins to slow, stop, and reverse course in a monumental event cosmologists call the Big Crunch. Everything collapses back in on itself, not into a tiny point of infinite density, but into a hot, dense state that then becomes the seed for the next Big Bang, the next great expansion, the next universe in the sequence. It's a breathtakingly beautiful and ancient idea, really the universe as a phoenix, perpetually dying in fire only to be born again from its own ashes. This isn't just philosophical musing, it's a serious scientific framework championed by leading physicists like Paul Steinhardt. In his view, our universe could simply be the latest iteration in an infinite series, each one leaving a faint but potentially detectable imprint on the next. So how could evidence of a previous universe possibly survive such a violent transition? The most promising clues are found in the oldest light we can observe, the cosmic microwave background radiation. This is the faint, cold glow that fills the entire sky, the cooled remnant of the universe's hot, dense infancy, captured when the first atoms formed nearly 14 billion years ago. When we map this radiation with incredible precision using satellites like Planck, we see it's not perfectly smooth. There are tiny, mysterious fluctuations in temperature, hot and cold spots that are the seeds of all future structure, the galaxies and clusters we see today. Some researchers, including the renowned mathematician Roger Penrose, propose that within these subtle irregularities could lie the fossils of a bygone cosmic era. Certain large-scale patterns and concentric circles of temperature variation in the CMB don't quite fit the standard model of a single, inflationary universe. Penrose and others suggest these anomalies could be the gravitational waves or shock waves generated by the collision of supermassive black holes in the universe that existed before ours. Imagine the final moments of a previous cosmos, a titanic struggle of collapsing giants sending ripples through the very fabric of space-time. Those ripples wouldn't be erased by the reset of a new Big Bang. They would imprint themselves onto the newborn universe, like a whisper from a forgotten world etched into the first light of the next. If this interpretation holds, then the cosmic microwave background isn't just a baby picture of our universe. It's a palimpsest, a canvas on which the final chapter of a previous draft is still faintly visible beneath the text of our own. This cyclical model completely transforms our perspective, turning the Big Bang from a singular, absolute beginning into a phase in an eternal, cosmic dance, a rhythm of creation and destruction on a scale so vast it challenges our very perception of time itself. But this idea of a single, cyclical cosmos is just one way to imagine a multiverse of drafts. Another, even more prolific mechanism might be constantly at work, generating new universes not in a sequence, but in a vast, ever-growing cosmic foam. This brings us to Alan Gough's revolutionary concept of inflation, and its even more mind-bending extension, eternal inflation. The standard inflationary theory tells us that a fraction of a second after the Big Bang, our universe underwent a staggering, exponential growth spurt, expanding faster than the speed of light and smoothing out the cosmos into the relatively uniform state we see today. But what if that inflationary period didn't have a clean, uniform ending everywhere? What if, in some regions, the conditions for inflation never switched off? This is the heart of eternal inflation. Picture not a single, expanding balloon, but an endlessly rising loaf of raisin bread where the dough itself is constantly expanding. Now imagine that most of this dough is still actively rising, expanding at an incredible rate. But every so often, in a random pocket of that dough, the yeast stops working. The expansion in that local region slows down and settles into a more stable, sedate pace, forming a bubble of normal space and time. Our entire observable universe could be just one such bubble, a single, stable region in an infinite, forever inflating background. And we are not alone. That eternally inflating background is constantly giving birth to new bubbles, each one a separate universe with its own Big Bang and its own unique set of physical laws. The cosmos becomes a bubbling cauldron of reality, a fractal and infinite landscape where new worlds are born every moment. The profound implication here is that these bubble universes aren't created equal. The random quantum fluctuations that cause a pocket to stop inflating and crystallize into a universe also determine its fundamental properties. In one bubble, the strength of the nuclear force might be slightly stronger, preventing hydrogen from ever forming and making stars impossible. In another, the cosmological constant could be so vast that space tears itself apart instantly. Our universe seems to have won the cosmic lottery, with constants perfectly tuned for complexity and life. Eternal inflation offers a powerful explanation for this fine-tuning. With an infinite number of bubbles, every possible combination of physical laws will be realized somewhere. We don't live in a special universe, we simply live in one of the habitable ones, a successful draft that emerged from the chaotic, generative foam of the eternal inflationary field. It's a humbling and awe-inspiring vision, suggesting that the very laws of nature we hold as immutable might just be local bylaws, applicable only within our own cosmic bubble. But if inflation creates a multiverse of simultaneous bubbles, and cyclic cosmology suggests a sequence of universes, could there be a bridge, a physical mechanism that actually connects one cosmic draft to the next? This brings us to one of the most fascinating and speculative ideas in all of physics, the potential for black holes to act as gateways. We know these cosmic monsters are formed when massive stars collapse, their gravity so intense that not even light can escape their pull. Everything that crosses the event horizon is seemingly lost forever, crushed into a point of infinite density called a singularity. It appears to be the ultimate end of the line, a one-way ticket to oblivion. But what if that's not the full story? The mathematics of Einstein's general relativity, the very theory that predicts black holes, also allows for the existence of their theoretical opposite, white holes. If a black hole is a cosmic drain from which nothing can return, a white hole would be a cosmic fountain, a region of spacetime that can only eject matter and energy, refusing to let anything back in. While we've never observed one, the equations are tantalizingly symmetrical. Now, imagine connecting the two. This is the concept of an Einstein-Rosen bridge, more popularly known as a wormhole, a theoretical tunnel through spacetime that could link the throat of a black hole in one universe to the mouth of a white hole in another. In this breathtaking scenario, the matter and energy swallowed by a black hole aren't destroyed. they're simply being transferred, like a cosmic recycling program where the waste from one universe becomes the raw material for another. A black hole in our draft could be funneling its contents into a white hole that represents the Big Bang of a brand new baby universe, creating a continuous loop of creation and destruction across cosmic epochs. This isn't just a wild thought experiment. Physicist Carlo Rovelli has applied the principles of loop quantum gravity to this problem and proposed a radical solution to the infamous black hole information paradox. This paradox arises because quantum mechanics says information can never be truly destroyed, yet black holes seem to violate this by obliterating everything that falls in. Rovelli's work suggests that the immense gravitational pressure inside a black hole might not actually create a true singularity. Instead, just before that point of infinite density is reached, quantum effects could cause a tremendous bounce, transforming the black hole into a white hole. This process would take an incredibly long time from an outside perspective, but it provides a mechanism for that swallowed information to be preserved and eventually radiated back out, not into our universe but potentially into another branch of reality. In this view, the faint Hawking radiation that slowly leaks from black holes might not just be random thermal noise. It could be a scrambled, encoded message, a data stream containing the quantum information of everything that ever fell in a relic, perhaps from a previous cosmic draft, slowly being transmitted into a new one. This idea fundamentally blurs the line between the end of one story and the beginning of another, suggesting that death and rebirth are not opposites but are inextricably linked in the grand, cyclical mechanics of the cosmos. Yet for all its destructive potential, dark energy might be only half of the evolutionary engine driving cosmic drafts. To understand the other half, we need to turn to a concept that governs the very arrow of time itself, entropy. Often described as the measure of disorder in a system, entropy always increases over time, a fundamental rule known as the second law of thermodynamics. In our universe, this means things inevitably move from a state of order to disorder. An ice cube melts in a warm room. A shuffled deck of cards never spontaneously sorts itself back into suits, and the entire cosmos is slowly but surely evolving toward a cold, dark, and uniform state known as heat death. This relentless march toward maximum entropy gives us a past and a future. It's the reason we remember yesterday but not tomorrow. But what if this inevitable slide into disorder isn't the final word for the entire multiverse? Some cosmological models, particularly those involving cyclic or bouncing universes, propose a truly radical idea that entropy could be reset. Imagine the universe not as a single, one-way journey from order to chaos, but as a cosmic sawtooth wave. Each draft begins at a point of incredibly low entropy, a state of exquisite order and structure inherited in some way from the endpoint of the previous cycle. It then expands and evolves, with entropy steadily increasing for billions of years, building galaxies, stars, and life, all while slowly running down. Finally, it reaches a state of maximum entropy, a featureless equilibrium. But instead of that being the end, a cosmic bounce or transition occurs, and a new universe is born, its entropy mysteriously reset to a low value once again, ready to begin the climb all over. Physicist Sean Carroll is a leading proponent of exploring how such a reset could be possible, suggesting that the endpoint of one universe might naturally give rise to the low entropy beginning of the next through processes we don't yet fully understand. This cyclical view of entropy offers a stunning explanation for why our universe appears so finely ordered and structured in its infancy. The cosmic microwave background is incredibly smooth and uniform, a hallmark of a very low entropy starting point. In a single, one-off universe, this is a profound puzzle. Why did the universe begin in such a special, unlikely state? But if our cosmos is just the latest in a long line of drafts, its orderly beginning isn't a mystery, it's an inheritance. It's a refined starting point passed down from previous iterations, much like how a master craftsman's final draft benefits from the lessons and mistakes of all the rough sketches that came before. The sandcastle from a previous day may be washed away by the tide, but the sand itself remains, its particles holding the memory of past structures, ready to be sculpted into a new, and perhaps even more complex, form by the next wave. By studying the interplay between dark energies shaping power and entropy's relentless drive, we start to see the outlines of a cosmic editing process, a set of fundamental forces that might not just govern a single universe, but guide the evolution of reality itself across countless drafts. Now, if we push this idea of the quantum vacuum even further, we arrive at one of the most startling mechanisms for creating an entire universe from what we would call nothing. This is the concept of vacuum decay. To understand it, we need to think of the vacuum not as a simple, empty state, but as a field that can exist at different energy levels. Picture a vast, tranquil valley surrounded by towering mountains. The state of our current vacuum is like a ball resting peacefully at the very bottom of that valley. It's stable, it's in its lowest possible energy state, and it's what we experience as the empty space of our universe. But what if our valley isn't the only one? What if there's an even deeper valley, a true vacuum with even lower energy, hidden on the other side of a mountain range? Our universe would currently be in what physicists call a false vacuum, a state that seems stable but is actually metastable. It's like that ball sitting in a small dip on the side of a much larger hill. It looks stable for now, but it has the potential to roll all the way down to a much lower point. The terrifying and magnificent part is that a quantum fluctuation could provide the tiny nudge needed to push that ball over the edge. If a random fluctuation in a tiny region of space provides enough energy, it could trigger a process called vacuum decay. A bubble of this new, true vacuum would spontaneously form, and then expand outward in all directions at nearly the speed of light. Inside this bubble, the fundamental laws of physics would be completely rewritten. The constants we rely on, the mass of an electron, the strength of gravity, would be different. This bubble wouldn't just be a new region of space, it would be the epicenter of a new Big Bang, the nucleation point for an entirely new universe with its own distinct properties, blossoming within the framework of our old one. The physicist Sidney Coleman did pioneering work on this, calculating how such a phase transition could propagate. The chilling implication is that if this process started somewhere in our cosmos, we would never see it coming. One moment, everything is normal. The next, an invisible wall of fundamental change is racing toward us at the speed of light, rewriting reality itself in its wake. For us, it would be an instantaneous end, but for the new cosmos born from that bubble, it would be a glorious beginning. This gives us a profound and almost paradoxical vision of cosmic origins. Our entire universe, with its hundreds of billions of galaxies, might itself be the product of just such a random quantum event within a much larger, pre-existing meta-universe or quantum foam. We are not the first draft, we are a draft written in the margins of another, far grander manuscript. In this view, the Big Bang wasn't a unique beginning from a singularity, but a local event, a fluctuation that achieved critical mass and blossomed into a full-fledged reality. And if it happened here, it has almost certainly happened elsewhere an infinite number of times. Each new bubble universe is a new cosmic draft, a new experiment in physics. Most of these drafts would be stillborn universes that collapse immediately, or whose laws are so unstable that no complexity can ever form. but by the sheer, staggering power of infinite chance. A few drafts like ours will randomly land on a set of laws that allow for stars, planets, and life. Our existence is not a planned outcome, but a statistical inevitability in a multiverse of infinite possibilities, a single successful trial in an endless cosmic experiment running on automatic. But if these cosmic drafts are out there, whether born from quantum fluctuations, eternal inflation, or black hole bounces, how could we ever hope to find tangible evidence for something that, by definition, exists beyond the boundaries of our observable reality? The answer might lie in the oldest light in the cosmos, a fossilized relic from the universe's infancy that could be hiding whispers from a time before time. This is the cosmic microwave background radiation, or CMB, a cold, faint glow that permeates all of space. It's the cooled remnant of the hot, dense plasma that filled the universe for the first 380,000 years after the Big Bang. When we point our most sensitive telescopes at it, we're essentially taking a baby picture of the entire cosmos. And just like a photograph, this image isn't perfectly uniform. It's speckled with tiny variations in temperature, minute hot and cold spots that are the seeds from which all galaxies, stars, and ultimately we would eventually grow. For the most part, these fluctuations align beautifully with the predictions of our standard cosmological model, a testament to the incredible power of modern science. But nestled within this overall agreement are a handful of strange, persistent anomalies that stubbornly refuse to fit the narrative. Certain large-scale patterns, like surprisingly large cold spots or curious concentric circles of temperature variation, appear statistically unlikely in a universe that began from a single, smooth, inflationary event. It's here that some of the most daring theoretical minds, like the renowned mathematician and physicist Roger Penrose, see a potential window into a pre-Big Bang existence. Penrose's conformal cyclic cosmology posits that the end of one universe, a vast, empty expansion dominated by massless particles, can become mathematically identical to the high-energy, dense beginning of another. In this model, the Big Bang is not a unique beginning but a conformal continuation, a transition he calls an aeon. If this is true, then the violent, energetic events that marked the death throes of a previous eon wouldn't just vanish. The gravitational shockwaves from the collision of supermassive black holes in that bygone era could have rippled through the fabric of space-time, imprinting themselves as distinct, circular patterns on the CMB of the next universe. These wouldn't be the subtle quantum seeds of our own universe's structure, but rather bold, cosmic-scale scars, bruises left on the newborn cosmos by the titanic struggles of its predecessor. Finding such patterns would be akin to an archaeologist discovering a fossilized bone that clearly belongs to a creature from a period long before life was supposed to exist. It would force a radical rewrite of our cosmic history, suggesting that our universe is not a solo performance, but merely the latest movement in an infinite symphony of creation. While these interpretations remain highly controversial within the scientific community, they represent a thrilling frontier, the possibility that we can actually observe the echoes of a forgotten draft, if only we know how to look for its signature in the ancient light. But what if these subtle patterns in the ancient light are more than just statistical quirks? What if they are actual fingerprints left on the glass of our newborn universe by something that came before? This is the extraordinary proposition put forward by some cosmologists, most notably the renowned mathematician Roger Penrose. He suggests that the most compelling of these CMB anomalies, particularly certain concentric rings of temperature variation, could be interpreted as gravitational shock waves. Imagine the final moments of a previous cosmic draft, a universe that had stretched into a vast, cold emptiness, its history written in the form of supermassive black holes. As that ancient cosmos met its end, these titanic objects might have collided in a last, monumental release of energy. The ripples from such an event wouldn't simply vanish. According to Penrose's conformal cyclic cosmology, they could traverse the transition between cosmic eons. In this model, the end of one universe, when stretched and smoothed through a mathematical transformation, becomes indistinguishable from the hot, dense beginning of the next. The Big Bang is not a true singularity but a conformal continuation, a rebirth. Those gravitational waves from a forgotten past would then imprint themselves onto the fabric of the new universe, leaving their signature as faint, circular patterns in the very first light it would ever emit. Finding such a pattern would be the cosmological equivalent of a paleontologist discovering a perfectly preserved dinosaur fossil in a layer of rock dating back 1 billion years before life even began. It would be an artifact completely out of its time, a clear signal that our standard story is incomplete. While many in the scientific community remain skeptical of this interpretation, the very fact that we can analyze the CMB with such precision to hunt for these ghosts is astounding. It turns our entire cosmos into a crime scene, and we are the detectives, using satellites like Planck as our magnifying glasses to search for evidence of a previous existence. This ancient light is no longer just a baby picture. It is a potential palimpsest, a cosmic parchment on which the final chapter of a dead universe is still faintly visible beneath the text of our own. The hunt for these fossils is one of the most thrilling frontiers in science, a direct attempt to peer beyond the veil of the Big Bang itself and answer the ultimate cold case. This takes us from the mind-bending physics of cosmic drafts to a question that strikes right at the heart of our own existence. What does it all mean for us? If our universe is truly just one draft in an endless cosmic library, it completely upends our traditional understanding of purpose and place. For centuries, humanity has largely operated under the assumption that we are at the center of a singular, created reality. But the multiverse theory, particularly the idea of an evolutionary process behind these drafts, offers a radically different narrative. It's a perspective that can feel both deeply humbling and strangely empowering. On one hand, it suggests our entire cosmos might not be a unique, divinely crafted masterpiece, but rather the one version that just happened to work, the survivor in a long chain of cosmic trial and error. We are not the center of everything. We are simply the inhabitants of a draft that was stable enough to last long enough for us to ask these questions. This is where the philosophical concept known as the Anthropic Principle becomes so crucial. Championed by thinkers like Nick Bostrom, it provides a powerful answer to the mystery of why our universe seems so perfectly fine-tuned for life. The constants of nature, the strength of gravity, the mass of an electron, the cosmological constant, are so precisely set that even a tiny change would make galaxies, stars, and life itself impossible. In a single universe, this seems like an unbelievable coincidence, a miracle, but in a multiverse of infinite drafts, it becomes a statistical certainty. If you have an infinite number of universes, each with randomly dialed physical constants, eventually one will, by pure chance, land on the winning combination. We shouldn't be surprised to find ourselves in a universe that can support us. We couldn't find ourselves in any other kind. It's like a puddle waking up and marveling at how perfectly the hole it occupies fits its shape without considering that the hole came first. The puddle is shaped by the hole, not the other way around. We are the puddle and our universe is the hole. To make this even more relatable, think of yourself as a character in a novel. You only have consciousness and awareness within the final, published edition of the book. But what about all the earlier drafts sitting on the author's hard drive? Perhaps in the first draft, your character was the villain and was killed off in Chapter 3. In the second draft, you might have been a completely different person with a different name and career. Those versions of you are just as real in the context of those drafts, but you, the conscious reader of the final book, would never experience them. You are only aware of the story in which you exist. This is precisely our situation if the cosmic drafts hypothesis is true. We are the characters who only exist in the one draft that worked out. This doesn't make our story any less meaningful. In fact, it might make it more precious. Our draft is the one where the author finally figured out the plot, where the characters found their voice, and where the narrative achieved a beautiful, stable coherence against all odds. This realization opens up a profound line of inquiry about other drafts. If our universe is the successful one, what happened in the others? Did some drafts flicker into existence with gravity too weak to form stars, becoming vast, empty expanses of scattered hydrogen? Did others have a strong nuclear force so powerful that all hydrogen fused into heavier elements instantly, leaving no fuel for stars to ever shine? And perhaps most hauntingly, could some of those failed drafts have, against even more impossible odds, given rise to life forms of a kind we cannot even conceive? Consciousness that exists in more dimensions, or beings made of pure energy in a universe where matter never coalesced. The possibility that other drafts might have contained their own fleeting, alien forms of intelligence adds a layer of poignant beauty to the whole concept. It transforms the multiverse from a cold, mechanical process into a grand, tragic, and awe-inspiring tapestry of experimentation, with our universe standing as one rare, shining success story. This perspective doesn't diminish our significance. It challenges us to find our own meaning and to cherish the incredible against all odds reality we get to call home. This notion of time as a wheel endlessly turning is perhaps one of humanity's oldest and most persistent intuitions. Long before telescopes or particle accelerators, ancient sages and philosophers gazed at the cycles of nature, the rising and setting sun, the passing seasons, the endless rhythm of birth, life, and death, and saw in them a grander cosmic pattern. In Hindu cosmology, time is not a straight line but a series of immense cycles known as kalpas. Each kalpa, lasting billions of years, is a single day in the life of the god Brahma, a period of creation and dissolution where the universe is breathed out and then inhaled back into its divine source, only to be breathed out again in a new form. The ancient Greeks had their own version of this with the concept of the Great Year, a vast cycle at the end of which the planets realign and a catastrophic renewal of the world occurs, wiping the slate clean for a new golden age to begin. These weren't just myths, they were sophisticated attempts to understand a universe that felt inherently rhythmic and regenerative. What's truly fascinating is how this ancient intuition is finding a startling new voice in the language of modern theoretical physics. Roger Penrose's conformal cyclic cosmology is a direct mathematical descendant of these ancient ideas. In his model, the distant heat-death future of our universe, a cold, empty expanse dominated by massless particles and stretched to incredible scales, becomes mathematically identical to the hot, dense, small-scale singularity of a new Big Bang. The end literally becomes the beginning in a seamless, conformal loop. Time, in this view, isn't broken by a definitive start or stop. It's an infinite series of eons, each one a self-contained universe with its own history, but each one connected to the next through this elegant geometric transformation. It's not a perfect, identical repetition like a clock striking 12, but more like a spiral where each cycle carries forward echoes and imprints from the one before. This is where the philosopher Friedrich Nietzsche's concept of the eternal return casts a long and haunting shadow. He proposed a thought experiment. What if a demon whispered to you that you would have to live this exact same life with every joy and every pain over and over again for all eternity? How would you feel? His point wasn't a literal prediction but a test of one's ability to affirm life in its entirety. The eerie resonance with cosmological models is undeniable. While the physics doesn't suggest an identical recurrence, every detail perfectly replaying, it does suggest a statistical one. In an infinite multiverse or an infinite cycle of time, every possible configuration of matter and energy will eventually repeat not once but an infinite number of times. The you that is reading this, the specific arrangement of atoms and experiences that makes you unique, will almost certainly happen again in some far future cosmic draft. This isn't about fate or predestination. It's about the sheer, staggering power of infinity and probability. If this is true, then the hidden drafts of the universe are not simply erased or stored away in some separate archive. They might be woven directly into the fabric of our current reality, like the faint, underlying text of a medieval palimpsest parchment that was scraped clean and reused, but where the ghost of the original writing still bleeds through. The concentric circles in the cosmic microwave background that Penrose studies could be one such ghostly layer, a direct imprint from a previous eon. The very laws of physics we take for granted might themselves be a composite, a best of compilation refined over countless iterations. This completely shatters our comfortable, linear perception of history. There is no absolute year one. There is no definitive beginning of time. There are only layers upon layers of cosmic history, each iteration writing its story over the last but never fully erasing it. We are not living in the first edition of existence. We are reading from a copy that contains fragments of all the drafts that came before, a living library of everything that ever was. But this journey through cosmic drafts leads us to one of the most profound and puzzling intersections of all, the point where the vast, objective machinery of the cosmos meets the intimate, subjective experience of the mind. Quantum mechanics, the rulebook for the very small, presents us with a bizarre and inescapable fact: the act of observation itself seems to play a role in shaping reality. The most famous demonstration of this is the double-slit experiment. When you fire tiny particles like electrons at a barrier with two slits, they don't just go through one or the other like little bullets. If no one is watching, they behave like waves, passing through both slits simultaneously and creating an interference pattern on the detector behind the barrier, a telltale sign that they've been in two places at once. But the moment you place a measuring device to determine which slit each electron actually goes through, this strange wave-like behavior vanishes. The electrons suddenly act like well-behaved particles, going through one slit or the other, and the interference pattern disappears. It's as if the particle knows it's being watched and changes its behavior accordingly. This isn't just a laboratory curiosity. It strikes at the very heart of what we mean by reality. It suggests that at the most fundamental level, the universe exists in a blurry, undefined state of pure potentiality, a superposition of all possible outcomes, until an observation forces it to pick one definite path. But what or who qualifies as an observer? Is it a machine, a human, a conscious mind? This is where the speculation ventures into truly deep waters. Some interpretations, like the one championed by physicist John Wheeler, take this a step further with his participatory anthropic principle. He famously suggested that we are not just bystanders in a pre-existing cosmos but participants in its creation. In his view, observers are necessary to bring the universe into a definite state of existence. It's a cosmic version of the old philosophical thought experiment. If a tree falls in a forest and no one is around to hear it, does it make a sound? Wheeler's quantum version might be, if a universe exists with no one to observe it, does it truly exist in a definite state? Apply this breathtaking idea to our concept of cosmic drafts, and the implications are staggering. It proposes that our conscious awareness might not just be a passive passenger in this particular draft of the universe, but an active editor in the cosmic process. Imagine the multiverse not as a static library of every possible book, but as a vast, branching choose-your-own-adventure story. At every quantum juncture, every moment where possibility exists, the story branches into countless different narratives. Your conscious observation, your measurement, your interaction with the world is what selects the branch you experience. In this view, the collective consciousness of all observers throughout history isn't just inhabiting this draft. It might be continuously collapsing it into existence, choosing this specific timeline out of an infinite sea of possibilities. This leads to a haunting question about all those other cosmic drafts we've been discussing. If a previous iteration of the universe unfolded with entirely different physical constants, but never developed any form of conscious life to observe it, did it ever truly become real in the way that ours has? Did it remain forever in a ghostly state of quantum potential, a draft that was written but never read, and therefore never fully actualized? Perhaps the reason our universe seems so finely tuned for life isn't just a product of cosmic natural selection, but a prerequisite for its very existence. A universe that cannot produce observers might remain forever unrealized, a mere possibility that never achieves the concrete reality that observation seems to demand. This idea beautifully and mysteriously bridges the cold, hard mathematics of physics with the warm, lived experience of philosophy, suggesting that our inner world of awareness might be inextricably woven into the outer fabric of the cosmos itself. We are not just living in the story, we may be essential to the act of its telling. But if reality is fundamentally mathematical, a vast and eternal landscape of abstract structures, how could we ever hope to find tangible proof? If other cosmic drafts aren't out there in space and time but exist in a timeless, Platonic realm, the very idea of detection seems almost paradoxical. Yet, this is precisely the thrilling challenge that scientists are beginning to grapple with. The search shifts from looking for physical artifacts to searching for anomalies, glitches in the matrix of our own universe that suggest its laws are not the only possible set, and that information might be leaking in from other mathematical structures. Imagine our universe as a perfectly self-contained software program. It runs on a specific internal code, our laws of physics. But what if, through some cosmic bug or a deliberate backdoor, we could find data that doesn't belong to our program? A piece of code written in a different programming language altogether. That would be the telltale sign of contact with another draft. This transforms projects like the search for extraterrestrial intelligence, or SETI, into something far grander. A search for extra-dimensional intelligence, or even extra-universal signatures. Instead of just listening for radio waves from other stars, we could expand the hunt to look for patterns in nature that are mathematically beautiful but physically impossible within our own framework. For instance, what if we detected a particle that defied conservation of energy not just temporarily, as in quantum fluctuations, but consistently? Or if we found a gravitational wave signal with a frequency and amplitude that simply cannot be produced by any known astrophysical event, like merging black holes or neutron stars. Such a signal might not be a natural occurrence at all, but a deliberate beacon, a message intentionally sent through a crack between mathematical realities by an intelligence that has mastered the architecture of existence itself. Physicists like Abraham Loeb have suggested that we should also be looking for physical artifacts, not just signals. These wouldn't be alien probes from another planet. but relics from before the Big Bang or from outside our cosmic bubble. One candidate is certain types of primordial black holes. Some could be remnants of a previous cosmic cycle, or even seeds from another universe that triggered our own inflation. Another possibility is the detection of exotic particles that don't fit into the standard model of particle physics. If we found a particle that could only be explained by a completely different set of force, strengths, or dimensions, it would be like finding a coin from a country that doesn't exist on any map of Earth. It would be physical evidence that our local mathematical structure is not the only game in town. This turns the entire field of cosmology into a form of deep time archaeology, where we're no longer just digging through layers of cosmic history, but sifting through the very source code of reality, hoping to find a comment left in the margin by a programmer from another draft. So if these cosmic drafts are real, how would we ever know? We've been looking for clues in the ancient light of the cosmos and the strange behavior of quantum particles, but what if the evidence is even more direct? What if we could find an actual artifact, a tool, a monument, or a message left behind by a civilization not from another planet, but from another universe entirely? This is the extraordinary premise behind expanding the search for technosignatures beyond the conventional hunt for alien radio signals. Technosignatures are any detectable signs of technology, and while we typically imagine them as transmissions from distant stars, they could theoretically be far more ancient and exotic. If a previous cosmic draft managed to spawn an intelligent civilization, and if that civilization reached a level of advancement we can scarcely imagine, they might have found a way to send something across the existential divide, a message in a bottle cast into the ocean of space-time, hoping it might wash up on the shore of a future reality like our own. The challenge, of course, is almost incomprehensible. We're not talking about decoding a signal from a few hundred light-years away. We're talking about finding something that predates the very foundation of our reality, an object or signal that somehow survived the death of one universe and the violent birth of our own. It would be like finding a fossilized bone in a layer of rock that formed before life itself began, an anomaly so profound it would force us to rewrite every textbook. Where would we even begin to look? Physicists like Abraham Loeb suggest we start by searching for physical objects that simply don't belong. One tantalizing candidate is a certain type of primordial black hole. Most black holes form from the collapse of massive stars, but primordial black holes are thought to be leftovers from the universe's incredibly dense and violent infancy. Some theories suggest they could have been forged in the first second after the Big Bang. But what if some weren't forged in our Big Bang? What if they are cosmic shrapnel, remnants of a previous draft that were caught in the transition and carried over into our new universe? Finding a black hole with properties that don't align with any of our models could be a sign that its origins lie elsewhere. Another possibility lies in the hunt for exotic particles. Our standard model of particle physics is a magnificent achievement, cataloging the known building blocks of everything we see. But what if we discovered a particle that simply doesn't fit? A particle that interacts with matter in a way that defies our understanding of the four fundamental forces, or that possesses a property we've never seen before. Such a discovery could be interpreted as a fragment of a different set of physical laws, a piece of a puzzle from a draft where gravity was stronger or the speed of light was slower. It would be like an archaeologist digging in Rome and unearthing a plastic widget. The material itself would be proof of a technology and an era that shouldn't exist in that context. These particles wouldn't necessarily be messages themselves, but they would be artifacts, evidence that our universe's laws are not the only ones that have ever existed. This transforms the entire field of cosmology from a purely theoretical pursuit into a kind of cosmic archaeology. We are no longer just astronomers looking at stars. We are detectives sifting through the rubble of existence, looking for clues to a cold case that predates time itself. Our tools for this dig are not shovels and brushes, but gravitational wave observatories like LIGO and Virgo, which could detect ripples from universe-shattering events in a previous draft. They are particle colliders like the Large Hadron Collider, which might accidentally create or reveal a particle that's a foreigner to our spacetime. They are telescopes like the new James Webb, which could spot anomalies in the distribution of the very first galaxies that hint at an influence from before the beginning. The search for extraterrestrial intelligence suddenly expands into a search for extra-universal intelligence, a hunt for not just who might be out there, but what might have been here before we even defined what here is. The possibility that we might one day hold a piece of another reality in our data, a relic from a forgotten draft, is perhaps the most thrilling and humbling prospect modern science has to offer. Now let's pause for a moment and consider the profound weight of this idea. What would it truly mean for humanity if we one day discovered definitive proof that our universe is not a singular creation, but merely one draft in an endless cosmic library? This revelation would ripple far beyond the laboratories and academic journals, shaking the very foundations of our philosophy, our spirituality, and our understanding of our own place in the grand scheme of things. It's a moment that would force a collective existential reckoning, not unlike the Copernican revolution that dethroned Earth from the center of the cosmos. That discovery was initially met with resistance and anxiety as it humbled us, showing we were not the literal center of God's creation. But in time, it also expanded our horizons, opening up a vast and majestic universe to explore. Evidence of cosmic drafts would be the next and perhaps ultimate step in that humbling yet enlightening journey. For many religious and spiritual traditions, this could present a fascinating challenge and an opportunity for renewed dialogue. Many creation narratives speak of a singular, purposeful act by a divine force, bringing forth one universe, one Earth, and one humanity. The idea of a multiverse of experimental drafts, some thriving and most failing, might seem at odds with that. Yet, it could also be interpreted as an even more magnificent and powerful expression of creation, not as a single, finite event, but as an ongoing, dynamic process of infinite creativity. The divine could be seen not as a clockmaker who built one perfect clock, but as a master artist endlessly experimenting, sketching, and refining. This wouldn't necessarily negate faith. It could deepen it, prompting new theologies that reconcile an infinite creative process with a singular creative source. It invites a conversation where science doesn't seek to erase spirituality, but to expand its canvas to an almost unimaginable scale. On a more personal, philosophical level, the immediate human reaction might be a chilling sense of insignificance. If we are just one of countless iterations, does our story lose its meaning? Does a single draft matter if there are infinite others? But this perspective misses a crucial point: the profound rarity and preciousness of a draft that works. If most universes are stillborn or barren, then a cosmos that allows for galaxies, stars, planets, and life is the ultimate cosmic lottery win. Our existence is not commonplace. It is spectacularly unlikely and therefore infinitely valuable. This knowledge wouldn't diminish our significance. It would reframe it. We are not the predetermined center of a single creation, but the lucky, conscious inhabitants of a successful experiment. This can foster a powerful sense of gratitude and a renewed determination to make our draft count, to honor the incredible statistical fortune that allowed us to be here at all. This leads directly to a compelling ethical consideration. a sense of cosmic kinship and stewardship, if we accept the possibility that other drafts might have, against even more impossible odds, given rise to their own fleeting forms of consciousness, it casts our own world in a new light. Those universes that collapsed too quickly or whose laws never allowed for life are like ghostly siblings to our own lost worlds, full of potential that was never realized. While we may never interact with them, their theoretical existence could inspire a deeper sense of responsibility for the one draft we know supports life, our own. It makes our universe not a disposable stage, but a rare and beautiful artifact that we have a duty to preserve. This cosmic perspective could be the ultimate argument for stewardship of our planet and our local cosmic environment, pushing us to think in terms of deep time and the legacy of our entire iteration of reality. Ultimately, embracing the concept of cosmic drafts doesn't have to be a cold, nihilistic exercise. It can be a source of immense wonder and a catalyst for a more expansive and compassionate worldview. It challenges our tribal instincts and our limited perspectives, reminding us that the story of existence is far bigger than any one narrative, any one planet, or any one universe. It prepares us for a future where our understanding of reality might be forever changed, not with fear, but with courageous curiosity and a humble acknowledgement that we are part of something so vast, its true nature is still unfolding before us. Long before physicists were drawing equations on blackboards about eternal inflation or conformal cycles, storytellers were exploring the haunting possibility of other worlds and altered realities. Science fiction, in its most powerful form, acts as a kind of collective dreaming, a safe space where we can play with these staggering concepts and experience their emotional weight long before we have the mathematics to prove them. Think about the twisted, paranoid realities of Philip K. Dick, where characters can never be sure if their world is real or just a convincing simulation. His work, like the novel that inspired The Man in the High Castle, doesn't just present an alternate history where the Axis powers won World War II, it forces us to ask a much deeper question. If such a world is real somewhere, what does that say about the choices we made in this one? Does it make our history less meaningful, or does it highlight the incredible fragility of the timeline we actually inhabit? These stories are laboratories for the soul, testing how we might feel and who we might become if the solid ground of a single reality suddenly gave way beneath our feet. This exploration has exploded into mainstream culture with the Marvel Cinematic Universe, which has brilliantly packaged the multiverse for a global audience. Films like Doctor Strange in the Multiverse of Madness or the mind-bending adventure of Spider-Man, No Way Home aren't just special effects spectacles. They are modern-day mythology, using superheroes as avatars to guide us through a cosmos of infinite possibilities. We see variants of beloved characters, a Doctor Strange who made a different choice, a Peter Parker who experienced a greater tragedy. These narratives make the abstract profoundly personal. They translate the dry scientific term, cosmic draft, into a relatable story about identity. If a different version of you is out there, more successful, happier, or perhaps a villain, what does that make you? Are you the product of your choices or merely the product of your circumstances? These stories suggest that in a multiverse, both are true simultaneously, and that's a profoundly disorienting yet liberating thought. Beyond the blockbusters, countless other stories serve as intuitive guides to these concepts. The novel Dark Matter by Blake Crouch is a masterclass in making quantum physics feel like a gripping thriller, as a man is thrust into a terrifying journey across countless versions of his own life. The television series Counterpart explored the geopolitical and espionage implications of a single, thin gateway to another Earth, asking how nations and individuals would react to their literal doubles. Even classic episodes of The Twilight Zone and Star Trek have used alternate realities to hold a mirror up to our own society, showing us who we are by showing us who we might have been. This is the true power of fiction. It allows us to conduct thought experiments on a grand scale. We can test-drive the emotional and philosophical consequences of a multiverse from the safety of our own homes, developing a gut-level understanding of concepts that would otherwise remain cold and abstract equations. This creative process doesn't just help the public understand science, it can sometimes inspire the scientists themselves. Many theorists grew up reading these very stories, their imaginations first sparked by tales of parallel worlds and time loops. The narrative logic of fiction can even suggest new formal possibilities. If a writer can imagine a mechanism for traveling between drafts, perhaps a physicist can later devise a mathematical framework for it. In this way, the relationship between science and science fiction is a constant dialogue. Science provides the rules of the game, and fiction eagerly plays within those rules, often pushing at the boundaries to see where they might bend. It acts as a testing ground not for the mathematical validity of a hypothesis, but for its human validity. It asks the question that pure physics sometimes forgets. If this is all true, what would it actually feel like? And by giving us an answer, it makes the universe, in all its possible iterations, a more wondrous and familiar place. The search for evidence of cosmic drafts is moving from the realm of pure theory into the domain of testable science, with a new generation of instruments offering our first real chance to find physical proof. This isn't about simply dreaming of other realities. It's about knowing where and how to look for their fingerprints within our own. The James Webb Space Telescope, for instance, is peering deeper into the early universe than ever before, mapping the formation of the very first galaxies. Scientists are meticulously analyzing this data, not just to confirm our models, but to find something that breaks them. What if the earliest galaxies are clustered in a pattern that can't be explained by standard inflationary physics? Or if they appear fully formed too quickly after the Big Bang? Such anomalies could be the cosmic equivalent of finding prehistoric fossils in a geologic layer where no life should exist, a tantalizing hint that the conditions for structure were not set solely by our universe's birth, but were perhaps influenced by a prior arrangement of matter and energy, a relic from a previous draft. On an even more fundamental level, giant particle colliders like the Large Hadron Collider are smashing matter together at incredible speeds, recreating the conditions of the early universe. While their primary goal is to find particles predicted by our standard model, the most thrilling discovery would be to find one that isn't. The detection of a so-called sterile neutrino or another exotic particle that simply doesn't fit into our current understanding of physics would be monumental. It wouldn't just be a new particle, it could be a refugee. Such an entity might operate under a different set of rules entirely, a stubborn leftover from a cosmic draft where the laws of physics were subtly or dramatically different. Finding it would be like an archaeologist discovering a perfectly machined steel gear in a Bronze Age dig site. The object itself would be proof of a technology and an era that shouldn't belong. Perhaps the most promising frontier in this hunt is gravitational wave astronomy. Observatories like LIGO and Virgo have already opened a new window on the cosmos by detecting ripples in spacetime caused by cataclysmic events like black hole mergers. The next step is to build even more sensitive detectors, like the planned Laser Interferometer Space Antenna, or LISA, which will be capable of sensing low-frequency gravitational waves from truly colossal sources. What are we hoping to find? A signature that stands out from the crowd. Most gravitational waves have a specific fingerprint based on the mass and spin of the objects that created them. but a signal that doesn't match any known astrophysical source. One that is too large, too slow, or has an inexplicable pattern could be something far more extraordinary. It could be the echo of a cosmic event that predates our universe, like the collision of two universe brains in a higher dimensional bulk, or the faint tremor from the final moments of a previous cosmic cycle. Scientists like Laura Mersini-Horton are actively working on the theoretical models that predict what such a signal might look like, providing a treasure map for experimentalists. This entire endeavor is akin to using a sophisticated metal detector on a vast cosmic beach. We are slowly sweeping our instruments back and forth across the sands of space and time, listening for the faint, metallic click that signals we've found something that doesn't belong, an artifact buried deep that hints at a history much richer and more complex than we ever imagined. The pursuit is its own reward, because even if we never find definitive proof, the process of looking forces us to refine our theories, sharpen our questions, and deepen our understanding of the one universe we can call home. This relentless drive to test the boundaries of reality is where the most profound discoveries are born. This incredible sensitivity to starting conditions isn't just a quirk of weather patterns. It might be the fundamental engine driving the wild diversity of potential cosmic drafts. Chaos theory, often illustrated by the famous butterfly effect, shows us how a minuscule change in a complex system, like the air disturbed by a butterfly's wings, can cascade through a series of events to ultimately alter the path of a hurricane weeks later and continents away. Now scale that idea up to the birth of a universe. The initial conditions set during the Big Bang, or whatever cosmic transition sparked our existence, were unimaginably precise. The rate of expansion, the balance of matter and antimatter, the strength of the fundamental forces, these weren't rough estimates, they were dialed in with a fidelity that defies belief. If even one of these parameters in a previous cosmic draft had been off by the most infinitesimal fraction, the entire story of that universe would have unfolded in a radically different direction, making it utterly unrecognizable to us. We can see a beautiful, everyday example of this principle in the formation of a snowflake. Each one begins as a mere speck of dust in a cloud, and as water vapor freezes onto it, the exact temperature and humidity at every microsecond of its journey to the ground dictate the formation of every branch and facet. No two are ever alike because the atmospheric conditions each one experiences are unique. Now, replace that speck of dust with a random quantum fluctuation in the seething energy of a newborn cosmos. In those first fleeting moments, the universe was a chaotic sea of potential, with quantum particles flickering in and out of existence. The specific way those fluctuations played out, which ones were amplified and which faded away, determined where the first slight over-densities of matter would form. Those tiny knots of gravity were the seeds for everything to come: the future galaxies, stars, and planets. In another draft, a different set of random quantum rolls of the dice would have planted those seeds in entirely different patterns, or perhaps failed to plant them at all. This perspective forces us to confront the stunning fragility and improbability of our own universe's success. The chain of events that led from a hot, dense singularity to a planet filled with life is so long and so delicately balanced that it seems almost miraculous. A draft where the strong nuclear force was a fraction of a percent weaker might have seen atomic nuclei unable to form, leaving the universe as a forever scattered soup of hydrogen. One where dark energy was slightly stronger could have torn space-time apart before the first star ever ignited. Our cosmos isn't just one possible outcome. It's a single, incredibly narrow path through a labyrinth of infinite possibilities, a path that somehow allowed for complexity and consciousness to emerge. The sheer dramatic variation between drafts from silent, empty voids to vibrant, complex worlds isn't a bug in the system. It's the inevitable product of chaos theory operating on the grandest possible scale. This understanding doesn't diminish our existence, it makes it all the more precious. The precision required to craft a universe that can support life is beyond calculation. It underscores that we don't inhabit a generic or average reality, but a spectacularly rare and refined one. Our cosmic draft is the snowflake that formed perfectly, against all odds, in the vast and stormy atmosphere of the multiverse. It's a successful experiment in stability, a testament to the fact that even within chaos, there can emerge islands of breathtaking order. This realization naturally leads us to wonder if anything of substance, any meaningful data or structure, can possibly survive the violent transition from one of these chaotic drafts to the next. One of the most perplexing puzzles in modern physics is the question of what happens to information that falls into a black hole. According to the rules of quantum mechanics, information can never be truly destroyed. It can only be transformed or rearranged. Yet a black hole, with its immense gravity, seems to violate this sacred principle by trapping everything that crosses its event horizon, seemingly forever. This is the famous information paradox, and it was Stephen Hawking himself who initially argued that black holes must destroy information, a conclusion that troubled him and the entire physics community for decades. But what if the solution to this paradox doesn't just apply to black holes, but to the entire cosmos? What if information isn't lost, but is instead preserved in a way we're only beginning to understand, potentially carrying data from one cosmic draft to the next? This is where the holographic principle enters the picture, and it's one of the most radical and beautiful ideas to emerge from theoretical physics. It proposes that all the information needed to describe a three-dimensional volume of space, every star, every planet, every person, can be entirely encoded on its two-dimensional boundary. Think of it like a security hologram on a credit card. The image appears to have depth and volume, but all the information to create that illusion is stored on a flat, two-dimensional surface. Now scale that idea up to a universal level. The holographic principle suggests that our entire three-dimensional universe, in all its vast complexity, might be a projection from information stored on a distant, two-dimensional surface that surrounds us. For our observable universe, that surface could be the cosmic event horizon, the farthest point from which light will ever have time to reach us. If this is true, it provides a breathtaking mechanism for how information could be preserved across the death of one universe and the birth of another. Stephen Hawking eventually revised his earlier view, concluding that information isn't annihilated by black holes, but is instead encoded in the Hawking radiation they slowly emit. Apply that concept to a cosmic scale, the chaotic, high-energy endpoint of a previous universe, a state that might look like a sea of boiling black holes merging and evaporating, wouldn't be a final erasure. Instead, all the information about that universe, every event that ever occurred within it, could be imprinted onto its boundary like data being written to a cosmic hard drive. Then, when a new universe is born from that collapse or quantum fluctuation, that information isn't lost. It becomes the foundational data from which the new reality projects itself. Imagine a technology company that never deletes its old servers. When they need to upgrade, they don't throw the old hardware away. They compress all the data into a massive archive file and use it as the seed for the new system. Our universe might be doing something similar. The information from previous cosmic drafts could be stored in a compressed, encoded form on the boundary of our reality, acting as the initial conditions from which our laws of physics, constants, and structures emerge. This wouldn't be a literal, readable history book, but a deep, mathematical imprint that subtly influences how our cosmos evolved. The very reason our universe has the specific constants it does could be because it inherited a kind of cosmic genetic code from its predecessor. This idea offers a stunningly elegant solution to the information paradox, while simultaneously providing a plausible mechanism for how drafts could influence one another. Information doesn't need to physically travel from one universe to the next. It's already there, baked into the fabric of space-time from the very first moment, defining the rules of the game. Decoding this data, learning to read the holographic imprint, would be the ultimate act of cosmic archaeology. It wouldn't just tell us about the history of our own universe. It could reveal the entire family tree of existence, allowing us to piece together the story of all the drafts that came before ours. The search for this code is already underway in the theories of quantum gravity, as physicists try to understand the language of reality written on the edge of the world. To truly grasp how our universe came to have its specific set of rules, we need to journey back to its earliest, most fiery moments, a time when reality was a seething, symmetrical soup of pure potential. In those first instants, the fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were not separate at all. They were unified into a single, perfect, and symmetrical superforce. There was no distinction between matter and energy, no atoms, no light as we understand it. Everything was one, but this state of perfect unity was inherently unstable, much like a pencil balanced perfectly on its tip. The slightest nudge, the smallest fluctuation, and it had to fall, breaking that perfect symmetry to find a more stable, albeit less symmetric, state. This cosmic process is what physicists call symmetry breaking, and it unfolded through a series of dramatic phase transitions, not unlike the everyday transformations we see when water freezes into ice or steam condenses into liquid. In the case of water, the liquid phase is highly symmetric. It looks the same in every direction, but when it freezes into a crystalline ice structure, that symmetry is broken. The water molecules lock into a specific, repeating pattern, choosing one particular orientation out of countless possibilities. The universe underwent a similar chilling and solidifying process, but on a scale and of a nature that is almost impossible to comprehend. As it expanded and cooled, the unified superforce could no longer maintain its perfect symmetry. It had to choose a path to break into the distinct forces that now govern our reality. Each break was a moment of cosmic decision, a fork in the road where the properties of our entire future were determined. The first major break might have separated gravity from the other forces. A subsequent one, perhaps occurring a fraction of a second later, split the electroweak force into the electromagnetic and weak nuclear forces we observe now. With every broken symmetry, new properties emerged. The particles that would eventually become quarks, electrons, and photons acquired their unique masses and charges. The very rules of the game were being written in these explosive moments of transition. This is why our universe has four fundamental forces and the specific particles it does. It's the direct result of how this sequence of symmetry-breaking events played out in our particular cosmic story. Now, let's extend this breathtaking idea to the concept of cosmic drafts. If our universe is just one iteration, it stands to reason that this process of symmetry breaking might not have unfolded the same way everywhere or every time. In a different draft, at that first critical moment of transition, the universe might have broken its symmetries along a completely different path. Imagine a tree with infinite branches. The trunk represents that initial, hot, symmetric state. As the tree grows, each branch represents a different way the symmetries could have broken. One branch might represent a universe where the strong nuclear force was significantly weaker, preventing atomic nuclei from ever forming and forever dooming that cosmos to a featureless haze of subatomic particles. Another branch might see electromagnetism and the weak force remaining unified, resulting in a reality where the processes that power stars are utterly different. The work of physicists like Alan Guth on inflationary cosmology gives us a potential mechanism for how these different branches, these alternate drafts, could actually physically exist. His theories suggest that the rapid inflation of the early universe could have been driven by a specific kind of phase transition in a quantum field. In the framework of eternal inflation, this process never truly stops. Different regions of the quantum foam stop inflating at different times and under different conditions. Each of these regions, each bubble universe, effectively experiences its own unique symmetry-breaking sequence as it crystallizes out of the inflating background. This means that each bubble inherits a different set of physical laws from the random quantum fluctuations that triggered its transition. One bubble becomes our universe with its 4 forces and specific particle masses. The bubble right next door could be a universe with 5 fundamental forces, or where photons have mass, or where the concept of mass itself doesn't even exist. This perspective transforms the cosmos from a single, fixed entity into a vast and ongoing laboratory of experimental physics. Our universe isn't special because it was designed to be this way. It's simply one possible outcome that happened to be stable enough to last for billions of years and complex enough to give rise to creatures who can ponder its origins. The specific charge of an electron, the exact strength of gravity, these aren't divine constants but more like local bylaws, applicable only within our cosmic bubble. By studying the delicate mechanics of symmetry breaking, we are essentially learning the grammar of creation, the set of rules that allows for an infinite plurality of realities to spring forth from a single, symmetric source. It shows us that the diversity of cosmic drafts isn't a bug in the system. It is the system working exactly as intended, generating every possible version of itself in a relentless creative explosion. Wrapping our minds around the sheer scale of cosmic plurality isn't just an intellectual exercise. It's a profound psychological event that can fundamentally reshape how we see ourselves. This shift in perspective from a singular, central reality to one of countless potential drafts can initially feel like a form of existential vertigo. It's the emotional equivalent of peering over the edge of a bottomless canyon, thrilling, but also deeply unsettling. For centuries, our foundational stories, whether religious or scientific, have placed us at the heart of a unique creation. To suddenly find ourselves as inhabitants of a single successful iteration in an endless multiverse can feel like a demotion, a loss of specialness that can trigger a deep-seated anxiety. It challenges the very core of our identity, making our personal struggles, triumphs, and even our history seem vanishingly small and insignificant against an infinite backdrop of alternatives. This is a natural human reaction to having our most fundamental understanding of home completely redefined. Yet, this initial feeling of insignificance is only one side of the coin. Flip it over and you find its opposite, a powerful and liberating sense of awe. The same infinity that can make us feel small also makes our existence here, in this particular draft, a statistical miracle of breathtaking proportions. Think of it not as being one of countless identical twins, but as the sole winner of the most improbable lottery ever conceived. If most cosmic drafts are stillborn, collapsing instantly, or expanding into cold, empty voids, or possessing laws that forbid any complexity at all, then the fact that we are here, in a universe that allows for galaxies, stars, planets, and conscious life, is the ultimate stroke of cosmic luck. This realization doesn't diminish our value, it reframes it entirely. Our story isn't cheapened because other drafts might exist. It becomes infinitely more precious because it worked. The air we breathe, the love we feel, the art we create, these aren't mundane occurrences in a generic reality. They are rare and beautiful flowers blooming in one specific, habitable garden amidst an infinite desert of impossibility. This shift in perspective from anxiety to awe is something we can actively cultivate. Just as astronauts who see Earth from space often report a transformative sense of connection and fragility known as the overview effect, contemplating the cosmic draft hypothesis can induce a kind of intellectual overview effect for the soul. Practices like cosmic meditation encourage us to sit with this vastness, to visualize the infinite tapestry of possibilities and find our own thread within it. The goal isn't to fully comprehend the infinite that's beyond our capacity, but to emotionally integrate its meaning. It's about moving from a place of fear, where we feel lost in the multiverse, to a place of wonder, where we feel connected to its grand creative process. This isn't a retreat from science, but an embrace of its most humbling and inspiring implications, allowing the data to transform not just what we know, but how we feel about our place within it all. This expanded view can also foster a profound sense of empathy and cosmic kinship. If we allow ourselves to consider that other drafts might have, against even more impossible odds, given rise to their own fleeting forms of consciousness, it casts our own world in a new and poignant light. Those universes that flickered out too quickly, or whose laws never allowed for a single thought to form, become like ghostly siblings to our own, lost worlds full of potential that was never realized. While we may never interact with them, their theoretical existence can inspire a deeper sense of responsibility for the one draft we know supports life, our own. It makes our planet not a disposable stage, but a rare and beautiful artifact that we have a duty to preserve. This perspective can be the ultimate argument for global stewardship, pushing us to think beyond national borders and short-term gains, and to consider the legacy of our entire iteration of reality. It challenges our tribal instincts, reminding us that in the grand scheme of existence, we are all incredibly fortunate tenants of the same precious, successful draft, and that alone is a powerful reason to treat each other and our world with greater respect and care. While physicists rely on complex equations and powerful telescopes to explore the concept of cosmic drafts, artists have long been mapping this uncharted territory with intuition, emotion, and sheer creative force. They provide us with a visual language for the unseeable, translating abstract theories into forms we can not only see but feel deep in our bones. Consider the intricate, mind-bending worlds of M. Z. Escher, where staircases loop in impossible ways and water flows perpetually uphill. His work isn't just a clever optical illusion, it's a profound meditation on the nature of reality itself, challenging our most basic assumptions about space, dimension, and perspective. In a very real sense, Escher was painting the architectural blueprints for a universe operating under a completely different set of physical laws, a draft where gravity is optional and logic is fluid. He gives us a direct, visceral experience of what it might be like to step into a reality where the rules are fundamentally foreign to our own. This tradition of cosmic cartography continues today with digital artists and creators who use modern tools to push the boundaries of visualization. Imagine a dynamic digital canvas where multiple potential universes are depicted not as separate spheres, but as translucent, overlapping layers of light and color. One layer might pulse with the vibrant gold and crimson of a universe dominated by violent star formation, while another shimmers in cool, tranquil blues and purples, a realm where dark energy has already smoothed everything into a silent, eternal haze. A third might fracture into impossible geometric patterns, representing a cosmos with extra spatial dimensions folded in on themselves. This kind of art does more than just show us an idea. It allows us to wander through it emotionally. It encourages a sense of cosmic empathy, a feeling for these other drafts as real places, each with its own unique mood, history, and aesthetic, even if they remain forever beyond our physical reach. Perhaps the most powerful fusion of these two worlds, the empirical and the expressive, is found in the groundbreaking collaborations between scientists and artists. Institutions like CERN, home to the Large Hadron Collider, actively host artist residencies, recognizing that creative minds can approach the same staggering concepts from a completely different angle and reveal facets that pure data might miss. The installations and artworks born from these partnerships are not mere illustrations, they are experiments in themselves. An artist might take the data stream from a particle collision and sonify it, turning the birth of a Higgs boson into an eerie, beautiful symphony, a sound from the first moments of our universe. Another might create a sculpture whose form is dictated by the equations of string theory, giving physical shape to the hidden vibrations theorized to underpin all of reality. In this sacred space where discipline meets, art transcends decoration and becomes a genuine tool for hypothesis generation. It allows researchers to experience their own theories through a different sense, to walk around them, and sometimes to see a new possibility hidden in the curves of a sculpture or the rhythm of a soundscape. This creative process is vital because it acknowledges a profound truth about understanding the cosmos. We are not merely logic engines. We are feeling, intuitive beings who learn through story, metaphor, and sensory experience. The cold, hard data telling us that other universes might exist is one thing, but to stand before a painting that evokes the lonely beauty of a failed draft, or to hear a musical composition that captures the chaotic energy of the inflationary epoch, is to understand that data on a human level. It satisfies a deep need to connect emotionally with the grandeur of these ideas, transforming them from intellectual abstractions into personal experiences. This fusion does not dilute the science, it amplifies it, creating a richer, more complete, and deeply moving understanding of our place within an infinite tapestry of potential existence. Art becomes the bridge between the mathematical possibility of cosmic drafts and the heartfelt wonder they inspire. But what if this relentless climb toward disorder isn't the final word for the entire multiverse? The concept of cosmic drafts offers a truly radical alternative, suggesting that entropy might not be a one-way street on the grandest of scales, but rather a cyclical process that gets reset with each new iteration of reality. In models of cyclic cosmology, the death of one universe and the birth of the next might not be a true ending, but a transformative phase transition. At the moment of this transition, whether it's a big crunch, a bounce, or a quantum tunneling event, the incredibly high entropy, disordered state of the old cosmos could be somehow wiped clean, providing the newborn universe with a fresh start of exquisitely low entropy. This isn't about reversing time or breaking the laws of physics. It's about the boundary conditions of existence itself being set anew, gifting each draft a pristine, ordered beginning from which its own arrow of time can then emerge and unfold. This process would create a fascinating, sawtooth-like pattern across the sequence of cosmic drafts. Picture a roller coaster slowly chugging up a steep incline, representing the universe starting in a state of perfect order and low entropy. As it reaches the peak, the long, thrilling descent begins. This is the universe evolving, with entropy steadily increasing as galaxies form, stars burn out, and complexity gives way to disorder. The ride ends in a chaotic, high-entropy scatter of cars and passengers. Now, imagine the track instantly resetting, and the roller coaster is once again at the top of that first hill, perfectly ordered and ready for another descent. Each cosmic draft is one complete ride on this roller coaster, with the reset mechanism at the bottom being the mysterious transition between universes. We, as conscious beings within this particular draft, are simply experiencing the ride on the way down, living in the period where entropy is actively increasing and creating the forward flow of time we perceive. This is precisely the framework physicists like Sean Carroll used to explain one of the most fundamental, yet often overlooked, mysteries of our existence: why we remember the past but not the future. Our brains, and indeed all processes within our universe, are subject to this increasing gradient of disorder. Memories are formed because entropy increases. A memory is a record of a more ordered past state that has since become more disordered. We can't remember the future because it hasn't happened yet. It represents a state of even higher entropy. This directionality isn't some abstract philosophical concept. It's a direct physical feature of our particular cosmic draft, a consequence of the specific low entropy initial conditions we inherited. It's the reason cause precedes effect, why an egg scrambles but never unscrambles, and why we feel time moving inexorably forward. This perspective opens up a dizzying array of possibilities for what other drafts might be like. If the entropy gradient defines our experience of time, then a universe that began with a different initial entropy value would have a completely different relationship with time itself. A draft that started with even lower entropy might have an arrow of time that feels even more forceful and deterministic to its inhabitants. Conversely, a universe that somehow began at a point of medium or high entropy might not have a clear arrow of time at all. In such a reality, the distinction between past and future could be blurry or even non-existent. Cause and effect might operate in reverse or in a chaotic, non-linear fashion. Beings in such a draft would have a consciousness utterly alien to our own, potentially perceiving time as a landscape to be wandered rather than a river to be swept along. This makes the study of entropy, and specifically the search for any anomalies in its expected behavior within our universe, a powerful tool for cosmic archaeology. If our low entropy beginning was indeed an inheritance, a gift from a previous draft, might there be subtle fingerprints of that handoff still embedded in the fabric of our cosmos? Could there be large-scale structures or residual energy patterns that seem out of place within our own entropy timeline, hinting at the disordered end state of the universe that came before? Finding such a signature would be monumental. It would be direct evidence that our universe is not the first draft, and it would provide a crucial clue for understanding the mysterious mechanics of cosmic rebirth. The hunt for these entropy-based signatures turns the entire cosmos into a historical document, and we are the readers trying to decipher the opening paragraph while searching for traces of the previous volume's final chapter. Now let's venture into one of the most mystifying corners of quantum physics, a phenomenon so bizarre that even Einstein famously dismissed it as spooky action at a distance. This is quantum entanglement, and it might just provide a tantalizing, if highly speculative, thread connecting the very fabric of different cosmic drafts. At its heart, entanglement is a connection that defies everything we know about classical reality. When two particles become entangled, they are no longer separate entities. They form a single, unified quantum system. You can then separate them by any distance imaginable across a lab table or across the galaxy, and they remain intimately linked. Measuring the property of one, like its spin or polarization, will instantaneously force its partner into a corresponding state, no matter how far apart they are. This isn't a signal traveling faster than light. It's a demonstration that at the most fundamental level, the universe is not locally real. The properties of these particles aren't fixed until they're measured, and the act of measurement itself seems to communicate across the vast gulf between them in a way that transcends space and time as we understand them. This profound strangeness, validated repeatedly in experiments like the seminal Bell test, has led some daring theorists to propose an even more expansive idea. If entanglement can create an instantaneous link between 2 points in our universe, ignoring the distance between them, could it also create a link that ignores the boundaries between universes? Imagine the multiverse not as a collection of isolated bubbles floating in some metaphysical foam, but as a vast, intricate spiderweb. Each strand of the web represents a connection, a thread of entanglement that might weave through the very foundations of spacetime itself, potentially tying our cosmic draft to others. A significant change or a quantum event in one draft could, in theory, send a subtle ripple or correlation through these entangled threads, creating a faint, detectable echo in another. It's a breathtaking thought. The birth of a star in a parallel reality might leave a minuscule, statistical fingerprint in the quantum noise of our own, a whisper from a world we can never directly see. The mechanism for this could lie in the very origins of the drafts themselves. If, as some models suggest, new universes are born from quantum fluctuations or black hole singularities in a pre-existing meta-universe, it's not a huge leap to think that the newborn cosmos might inherit some quantum connections from its parent. Particles in the new draft could remain entangled with particles in the old one, or with particles in sibling drafts born from the same quantum event. This would create a permanent, if subtle, quantum tether, a hidden channel through which information, in its most raw form, could be shared. It wouldn't be a channel we could send a message through, but rather one that creates a fundamental, underlying correlation between the drafts, like two instruments in an orchestra that have been perfectly tuned to the same resonant frequency, forever humming in sync across the void. Exploring this possibility pushes the very limits of physics and forces us to reconsider what we mean by information. In our universe, quantum information is never lost. The holographic principle suggests it's preserved on our cosmic horizon. If entanglement does connect drafts, it could be the mechanism by which this informational inheritance is passed along. The quantum state of a previous universe, encoded in its final moments, could be transferred via these spooky connections to imprint the initial conditions of the next, providing the low entropy starting point that seems so finely tuned. This turns entanglement from a mere curiosity of the quantum world into a potential cosmic architect, a fundamental force weaving the tapestry of reality across multiple iterations and ensuring a thread of consistency runs through the entire multiversal sequence. Of course, this remains one of the most speculative ideas in all of cosmology. Proving it would require detecting a correlation or anomaly in our universe that has no possible cause within our own spacetime, a signature that points unequivocally to an influence from outside. We are far from having the technology or the theoretical framework to even know what to look for. Yet, the mere possibility is incredibly inspiring. It drives physicists to develop new models of unified physics, theories that can seamlessly blend quantum mechanics with gravity and perhaps provide a mathematical language for describing these trans-universal links. The pursuit itself, whether it ultimately proves true or not, expands our imagination and deepens our appreciation for the profound, interconnected weirdness that may lie at the heart of all existence. But what separates a cosmic draft that endures for billions of years from one that flickers out of existence almost immediately? The answer lies in the delicate and seemingly miraculous fine-tuning of the universe's fundamental constants. Imagine a vast cosmic control board with dozens of dials, each governing a different aspect of reality: the strength of gravity, the mass of an electron, the precise value of the cosmological constant. In most potential universes, these dials are spun randomly, and the results are almost always catastrophic. A universe where the strong nuclear force is just a fraction weaker might never form stable atomic nuclei, dooming it to remain a forever scattered, lifeless haze of protons and neutrons. One where dark energy is slightly more powerful could tear space-time apart in a violent, big rip before the first star ever has a chance to ignite. Our universe, by contrast, appears to have all its dials set to exquisitely precise values that allow for a long, complex, and structured evolution. This isn't just a happy accident, it's the hallmark of a draft that has passed the ultimate test of cosmic sustainability. This incredible fine-tuning naturally leads to a powerful and elegant theory: cosmological natural selection, proposed by physicist Lee Smolin. Think of it not as a single creation event, but as an ongoing evolutionary process operating on a scale almost impossible to comprehend. In Smolin's model, universes aren't just born, they can actually reproduce. The mechanism for this cosmic procreation is the black hole. When a massive star collapses into a black hole, the singularity at its heart might not be a final state of oblivion. Instead, it could serve as the seed for a new Big Bang, giving birth to a brand new baby universe in a realm of space-time forever separated from our own. This new universe wouldn't be an identical copy of its parent. Just as in biological evolution, there would be small, random variations, slight tweaks to the physical constants inherited from the parent universe. This is where the engine of natural selection kicks in. A universe that is stable and long-lasting like our own has the right conditions to form not just stars, but generations of stars. It can forge heavy elements in stellar furnaces and scatter them across space in supernova explosions, providing the raw material for planets and, potentially, life. Crucially, a universe like this also produces a prolific number of black holes. A universe that is finely tuned for longevity is, by definition, also a universe that is highly fertile, producing many offspring that carry its successful traits forward. Conversely, a poorly tuned universe, one that collapses back on itself too quickly or expands so rapidly that matter is ripped apart, would produce few or no black holes. It would be a cosmic dead end, a failed draft whose unstable constants are effectively edited out of the multiversal gene pool. Over countless iterations, this process would inevitably select for universes that are stable, long-lived, and complex. We don't live in a special universe, we live in a successful universe, a proven survivor in the unforgiving arena of cosmic evolution. This transforms our perspective on the cosmos from one of passive observation to active investigation. Cosmology becomes a form of evolutionary biology, where we can study the traits of our universe as adaptations honed over deep time. The specific charge of an electron, the exact strength of gravity, these aren't arbitrary divine decrees. They are the cosmic equivalent of a giraffe's long neck or a cheetah's speed, highly refined solutions to the challenge of survival and reproduction. By understanding these traits, we can make predictions. For instance, if Smolin's theory is correct, we should expect that any changes to the constants in a child universe would be very small, as large mutations would likely be fatal. We might also predict that the laws of physics in our universe are optimized for the production of black holes, not for the convenience of life. life, then, becomes a fascinating byproduct of a cosmos that is successful for other, more fundamental reasons. This framework provides a stunningly powerful and non-mystical explanation for the greatest puzzle of all. Why does anything we see around us even work? Long before telescopes or particle accelerators, humanity was already dreaming of multiple worlds and cyclical existences, using the only tools available at the time: myth, philosophy, and a deep, intuitive observation of the natural world. These ancient narratives weren't primitive fantasies. They were profound, pre-scientific attempts to explain the cosmos and our place within it, and they reveal a startling prescience about ideas we now explore with mathematics. Consider the vast timescales of Hindu cosmology with its concept of kalpas. A single kalpa, a day in the life of the god Brahma, lasts over 4 billion years, a period of creation that eerily aligns with the age of our own Earth. After this immense day comes the pralaya, the night of dissolution, where the universe is systematically reabsorbed. This isn't a final end, but a pause before the cycle begins anew with the next dawn. Similarly, Norse mythology gives us Ragnarok, a cataclysmic series of events featuring a great winter, the death of gods, and the world consumed by fire and water. Yet from the ashes, a new, fertile world emerges, and a new generation of gods and humans inherits it. These stories, born on opposite sides of the globe, share a common, haunting thread. The universe is not permanent but periodic. It dies and is reborn not once, but in an endless, rhythmic loop of destruction and creation. This intuition extended beyond mythology into the realm of early philosophy. In the 6th century BC, the Greek philosopher Anaximander proposed a concept that feels astonishingly modern. He suggested that the fundamental origin of everything was not a familiar element like water or fire, but the apeiron, the boundless, the infinite, the indefinite. From this formless, eternal source, he believed, multiple worlds naturally emerged, existed for a time, and then dissolved back into the boundless, only for the process to repeat infinitely. He saw the universe not as a singular event, but as one of countless, cyclical occurrences springing from an eternal, underlying reality. This idea of infinite worlds arising from a primordial, quantum-like foam is a breathtaking leap of reasoning for its time, a philosophical precursor to the multiverse theories we grapple with today. It shows that the human mind has, for millennia, been uncomfortable with the idea of a solitary, unique cosmos, instinctively feeling that our reality must be part of a much larger, more complex tapestry of existence. What's truly remarkable is the continuity of this quest. The fundamental questions have remained the same for thousands of years. Did our world have a beginning? Will it have an end? Are we alone? The only thing that has changed is our toolbox. We've traded the poetic metaphors of gods and world serpents for the precise language of mathematics, the narratives of myth for the testable predictions of quantum field theory and general relativity. Ancient stargazers looked at the rhythmic cycles of the moon, the seasons, and the stars and extrapolated a cyclical cosmos. Today, we look at the redshift of galaxies, the fluctuations in the cosmic microwave background, and the equations of eternal inflation, and arrive at a strangely similar conclusion. Existence is likely plural and cyclical. The core intuition has been refined and given rigorous form, but the awe-inspiring wonder at the vastness of it all remains identical. This historical journey reminds us that our modern scientific pursuit is not a break from tradition, but the latest chapter in a timeless human story, the story of us trying to understand where we came from and what else might be out there. This deep historical context makes the concept of cosmic drafts feel less like a radical, newfangled idea and more like a natural evolution of a very old and persistent human suspicion. We have always, in some way, felt that our version of reality might not be the only one. This long arc of thought, from the poetic visions of ancient seers to the complex calculations of modern cosmologists, connects us to every human who has ever looked up at the night sky and felt that quiet, irresistible pull of curiosity. It grounds our cutting-edge science in a rich, philosophical tradition, showing that the desire to peer beyond the veil of our immediate perception is an essential part of what makes us human. And as we stand on the shoulders of all these thinkers, from Anaximander to Penrose, we are now equipped to ask the next, even more daring question that has simmered within these myths and theories all along. If these other drafts are real, could we ever hope to speak to them? But if these cosmic drafts are real, separated from us by the ultimate firewall of a different Big Bang or a shift in the very laws of physics, could we ever hope to do more than just theorize about them? Could we actually send a message or even receive one? The idea of inter-draft communication sits at the very edge of theoretical physics, a dream that pushes our understanding of reality to its absolute limits. The most commonly imagined bridge is the wormhole, a hypothetical tunnel through the fabric of spacetime that could, in principle, connect two distant points or even two separate universes. The mathematics of general relativity allows for such structures, but they would require a form of matter with negative energy density, something we have never observed, and that may be completely impossible to stabilize. Even if we could create or find a wormhole, keeping it open long enough to send a single photon through without it collapsing instantly is a challenge that may forever remain in the realm of equations on a chalkboard. Another potential avenue lies in the quantum realm with the bizarre phenomenon of quantum tunneling. This is where a particle can seemingly defy classical physics and pass through an energy barrier that it shouldn't have the ability to cross. Some theorists have speculated that if the quantum fields that make up our vacuum are in a false state, as we discussed earlier, it might be possible for information to tunnel through the energy barrier separating our vacuum from a different one. But this isn't like sending a radio signal. It would be more like a random, scrambled piece of data spontaneously appearing in the quantum noise of another universe, with no way to control its source, destination, or content. The signal would be indistinguishable from random background fluctuations, a single drop of water appearing in a stormy ocean with no way to know where it came from. So if traditional physics offers such faint hope, where does that leave us? Perhaps the answer isn't in building a transmitter, but in becoming incredibly sophisticated listeners. Imagine standing on the edge of a vast, deep canyon and shouting. Your voice echoes off the walls immediately around you, but you might also hear a much fainter, delayed echo coming back from a parallel canyon on the other side of the mountain range, a sound that has traveled a much longer, more complex path. In a cosmological sense, our most sensitive instruments for listening to these faint echoes are gravitational wave observatories like LIGO and Virgo. These detectors are already listening to the ripples in spacetime caused by colossal events like black hole mergers. A truly exotic event, like the collision of two universes themselves in a higher dimensional bulk space, could theoretically send a gravitational shockwave through the multiverse, leaving a distinct and unmistakable signature in our detectors. It would be a sound unlike any other, a deep cosmic thud with a frequency and amplitude that simply cannot be produced by any known astrophysical event within our own universe. This pursuit captivates visionary physicists like Michio Kaku, who often speaks about the potential for a Type 4 civilization, a society so advanced it has mastered the physics of the entire multiverse. For such a civilization, communicating across cosmic drafts might not be a fantasy, but an applied science. they might have learned to manipulate the fundamental constants in their local region of space to send modulated signals through the quantum foam or to create stable wormholes as cosmic telegraph wires. While this is the stuff of far future science fiction for us, the very act of considering it pushes our own technology forward. The dream of detecting such a signal, however faint, drives us to build more sensitive quantum sensors, more powerful particle colliders, and more advanced space telescopes. It fuels innovation in quantum computing, as we might need such immense processing power to even recognize a message from another reality, if it were hidden in the seemingly random fluctuations of the vacuum or the cosmic microwave background. This transforms the search for extraterrestrial intelligence into something even grander, the search for extra-universal intelligence. It adds a thrilling, almost poetic goal to the scientific endeavor. We are not just looking for neighbors on other planets, we are scanning the static of existence itself, hoping to find a pattern that says, "You are not alone in the multiverse." The idea of cosmic pen pals, of sharing knowledge with a civilization that experiences a completely different set of physical laws, is perhaps the most ambitious dream humanity has ever conceived. It redefines exploration, turning it inward to the very laws of physics and outward to the infinite possibilities that may lie beyond our cosmic horizon. So where does all of this leave us, right here and right now, in the quiet moments of our own lives? It's one thing to marvel at the grand physics of cosmic drafts, but it's another entirely to feel its meaning resonate in your own chest. This isn't just a story about the universe out there. It's a mirror held up to the universe within us, to our choices, our regrets, our hopes, and our singular, precious path. If the multiverse is real, then every decision you've ever hesitated over, every road not taken, isn't just a ghost in your mind. In another draft of reality, that ghost is living, breathing flesh. Another version of you did take that job, move to that city, or say what you left unsaid. Their life is unfolding in a world just as real as this one, shaped by a choice you made differently. This realization can feel like a double-edged sword. On one hand, it could make our own choices seem less significant. If every possibility is realized somewhere, then what makes this path special? But flip that perspective and you find its beautiful opposite. The fact that you are here experiencing this specific timeline with all its unique joys and sorrows makes it incredibly rare. You are not a generic consciousness. You are the specific you that emerged from a near-infinite series of events to be reading these words at this exact moment. The life you are living is not diminished by the existence of others. It is made unique. It's the difference between being the only book in the library and being one of millions. In the first scenario, your story is all there is. In the second, your story is the one you get to hold, and that makes it infinitely more valuable to you. This can be a powerful antidote to regret. We all carry the weight of paths untrodden, wondering how our lives might be different if we had made another choice. The concept of cosmic drafts offers a form of liberation. It allows you to acknowledge that other outcomes do exist, just not in your current reality. That version of you that pursued a different career or married a different person is living that life elsewhere. This isn't about dismissing your current reality, but about freeing yourself from the paralyzing grip of what if. It allows you to release the alternative timelines as valid stories that are simply being told in another room, which in turn allows you to fully invest in. Appreciate the story you are actually living. It's a call to stop comparing your life to an imaginary ideal and start cherishing its authentic, one-of-a-kind texture. Ultimately, this isn't a philosophy of passive observation, but one of active participation. Knowing that our universe is one draft among many doesn't mean we should just sit back and let things happen. Quite the opposite, it charges us with a profound responsibility. If we are the conscious inhabitants of this particular iteration of reality, we become its curators. We have the ability and perhaps the duty to make this draft a good one, to strive for kindness, to pursue understanding, to protect the fragile beauty of our world, and to push the boundaries of knowledge and creativity. We are the universe becoming aware of itself, and with that awareness comes the power to shape its local expression. Our choices matter not in spite of the multiverse, but because of it. We are writing a chapter in a cosmic story, and our collective actions determine whether this draft is remembered by us, right here, as a tragedy, a comedy, or a triumphant tale of growth and discovery. It invites a quiet, daily awe, a sense that the mundane and the cosmic are intimately linked, and that by living with curiosity and compassion, we are honoring the incredible statistical fortune that placed us in a draft where such things are even possible. And so we find ourselves at the end of this incredible journey, having ventured from the very first moments after the Big Bang to the farthest edges of theoretical physics and philosophical wonder. We've walked through the echoing halls of cyclic cosmology, where universes breathe in and out in an eternal dance of expansion and contraction. We've peered into the chaotic, bubbling foam of eternal inflation, where new cosmic drafts are born every moment in a vast, unending multiverse. We've stood at the precipice of black holes, contemplating their role not as endpoints, but as potential gateways, cosmic recycling centers funneling the material of a dead universe into the birth of a new one. We've sifted through the oldest light in the cosmos, the cosmic microwave background, searching for those faint, ghostly imprints, the cold spots and concentric rings that might just be the fossils of a universe that existed before our own. The evidence, while still speculative, paints a picture of a cosmos far grander and more mysterious than we ever imagined. It suggests that our universe might not be a singular, static creation, but a dynamic, evolving entity, one successful draft in an endless library of possibilities. This isn't just a scientific hypothesis, it's a profound shift in perspective. It redefines our place in existence, moving us from the center of a single, created stage to the conscious inhabitants of a rare and precious iteration of reality. We are not less significant in this vast multiverse. We are more so because we are the lucky ones. We won the cosmic lottery, emerging in a draft with the exact right conditions to allow for galaxies, stars, planets, and life to form. Every breath we take, every thought we have, is a testament to that incredible, against all odds fortune. This journey reminds us that science is more than a collection of facts and figures. It is the ultimate expression of human curiosity. It's our species' way of reaching out into the darkness and asking the biggest questions we can conceive. The pursuit of these ideas, even without definitive proof, expands our imagination and deepens our connection to the cosmos and to each other. It fosters a sense of humility and awe, reminding us that there is still so much to learn, so many mysteries left to unravel. So I encourage you to carry this sense of wonder with you. Look up at the night sky not as a ceiling, but as a window into a past littered with the ghosts of other universes and a future brimming with infinite possibilities. Let it fuel your own questions, your own explorations, and your own conversations about the nature of everything. Your thoughts and perspectives are a vital part of this ongoing discovery. This conversation doesn't end when the video does. I truly want to know what you think. Does the idea of cosmic drafts resonate with you? Do you believe there were versions before this one? Share your thoughts in the comments below. Let's keep this discussion going. If this exploration sparked your curiosity, if it made you see the world a little differently, then please consider liking this video and sharing it with someone else who marvels at the mysteries of the universe. And subscribe to the channel so you don't miss our next deep dive into the wonders of space, time, and reality itself. Thank you so much for joining me on this adventure. Never stop asking, never stop wondering, and above all, never stop exploring.